Hello everyone, my name is Fabien Gaskoviak. Let me present my work entitled Evaluation of Robot Navigation Among People, which presents an original use case of virtual reality. This work is part of the European H2020 Crowdbot project. The Crowdbot project was built to address the freeze robot problem, formally described by Trotman in 2010. Robots such as this delivery robot are expected to perform safe navigation, potentially very close to moving people. In such cases, robots will have to stop as soon as an imminent collision hazard is detected, taking into account human motion prediction uncertainty. Once your environment surpasses a certain level of complexity, any path will be considered unsafe, and the robot freezes in place. Since a feasible path typically exists, this behavior is suboptimal and might lead to dangerous situations. For instance, the robot might block an exit door during an evacuation, which is not acceptable. In order to solve this issue, it is necessary to improve the precision of the human motion prediction as well as the motion planning of the robot. To assess the planner performances in situations of near collision, an evaluation protocol taking the presence of humans into account is required. In the literature, for instance with the frozen planner, the method of evaluations consists in performing real condition experiments where the robot is in the crowd. Such real conditions experiments might be difficult to perform, especially if the robot is heavy or bulky, or moves with a lot of energy. For instance, with this security robot, which weighs 136 kilograms, near-collision human-robot interactions is hardly doable in experimental conditions without raising ethics issues. Another example is the experimentation with autonomous buses, which are powerful, thus dangerous in crowded environments. To evaluate robot behavior, it is possible to use simulation instead. For instance, on this video showing the Crowdbot simulator, a simulated robot moves through a simulated crowd. The main issue is that human reaction to robot is really difficult to capture when using a simulation algorithm. Similarly, the robot's sensing capabilities, its information processing capabilities and mechanical behavior, its dynamics, is hard to capture. In the end, a simulation is quite limited in its capacity to simulate human-robot interactions, and real condition experiment is always required. To keep the safety brought by the simulation and the realism of real condition experiments, our idea is to use virtual reality to immerse both a human and a robot to create a virtual interaction. The use of virtual reality for robotics applications is not new. For instance, the collaborative robot is being controlled by an operator using virtual reality. However, to the best of our knowledge, no human-robot interaction studies involve both the robot and the human fully immersed in the virtual world. Our proposition is to use virtual reality in a way that the realism of the interaction is kept intact and no simulation of the robot nor the human is required. In addition, we have the usual benefits of virtual reality, that is, keeping control over the experiment regarding the data collection or repeatability. Finally, we guarantee a safe and collision-free experience during near-collision human-robot interactions. The main novelty in our work is to immerse together the human and the robot in the virtual environment. Immersing a human is usual here, but immersing a robot will enable us to keep the realism of its way to sense the human motions and the way it reacts accordingly. It allows us to use any robot without the need to model it. It allows the robot to interact with the virtual world as if it was a real world. Our first contribution is the new use of virtual reality to immerse the human and the robot. Our second contribution is a pilot study to assess our virtual reality platform capability of delivering non-biased experimental data. There are 3 workspaces in our platform. a physical participant workspace, a virtual interaction workspace, and a physical robot workspace. The physical participant workspace is the place where the participant is present, alone, and is allowed to move freely without risk of collision. In this place, the participant body motion is tracked and broadcasted to the virtual interaction workspace. In the virtual interaction workspace, an avatar replicates the human participant motion in real time. The third workspace is the physical robot workspace. It is the place where the robot can move without risking collision with humans or obstacles. Again, the robot motion is tracked, and motion data is broadcasted to the virtual interaction workspace. The virtual place where the participant avatar already is now also have a robot avatar which replicates the robot motion. Now, in terms of perception, the virtual interaction workspace is graphically rendered from the point of view of the human avatar and displayed to the human using a HMD. Doing so, the participant can perceive the robot motion in the virtual place. Concerning the robot, its sensors are simulated in order to perceive the virtual world as a real one. This figure shows the technical complexity of the platform. You can retrieve the same workspace I just described. Formally described in the paper, this figure shows the different components we used for the pilot study: the tracking system Vicon and Xsense, a FOV HMD, the robot Pepper and the sensors we simulated, and how everything is connected. In the end, while the robot and the participant are physically separated in their respective workspaces, they perceive a virtual interaction as if they were in close proximity. Our second contribution is the pilot evaluation of the bias in human-robot interaction experiments performed in virtual reality. Our objective is to find out if data collected during near-collision human-robot interaction experiments are biased due to the system I just described. The objective is ambitious. Thus, we decided to remain very simple and run a pilot study with two simple tasks. First, our robot is moving in a sinusoidal movement back and forth. Participants were asked to follow the robot. Second, participants were asked to lead the movement and move back and forth. Both tasks were performed using our virtual reality platform and in real conditions. I'll now present a trial of the study to illustrate the tasks and the conditions. First, the robot leads the interaction in real conditions. Then, with our virtual reality platform. Second, the human leads the interaction in real conditions. Then, with our virtual reality platform. To evaluate our system, we use the robot Pepper, a humanoid robot which is lightweight and moves slowly, thus is safe to use with participants. For the robot to be able to perceive the virtual environment, we had to simulate some of its sensors: the front camera, the 3D sensor, the laser sensors, the infrared sensors, the sonar sensors, and the bumper. For this study, our hypotheses are: in virtual and real conditions, the trajectories of the participant and the robot will be highly correlated over time. The virtual condition will induce a higher reaction time from the robot and the participant than the real condition. And finally, in virtual condition, the human speed will be lower than in real condition, as it is a commonly observed fact. For the results, the first hypothesis was that in virtual and real conditions, the trajectories of the participant and the robot will be highly correlated over time. To evaluate this, we used cross-correlation. In signal processing, Cross-correlation is a measure of similarity of two time series as a function of displacement of one relative to the other. On this example, the time series G is being delayed up to a point where the time series F and G are the same. This gives us the higher correlation associated to a delay corresponding to the displacement of the time series G. What we found is that for each trial of each task in each condition, the trajectories were similar to the example trial shown here, and were highly correlated. For instance, in the example here, the correlation was 0.95. We expected a higher reaction time in virtual reality. The computed delays are part of the cross-correlation results. We find that for the task 1, where the robot leads and the human follows, the delays are close to 0 in real condition as well as in virtual condition, which contradicts the hypothesis. We explain this by the fact that the robot paper was moving slowly, and the participant had plenty of time to follow the robot motion. We also believe that the repetitive motion helped the participants to anticipate the robot motion. The second task, where the robot follows, shows slightly higher delays in virtual reality than in real condition, which goes in the direction of our hypothesis. We think that the two tasks have different results because the participant anticipated the movement, while the robot was not capable of doing so and was purely reactive. For the third hypothesis, we expected that the human speed will be lower in the virtual condition than in real condition, as it is a commonly observed fact. We find that we cannot conclude for the moment. The difference in speed between the two conditions was not significant. Also, we noticed that the robot was moving a bit faster in virtual reality conditions than in the real condition. The graph represents the average speed of the robot for the task where it leads the motion. In blue, the task is performed in VR, while in red, the task is performed in real condition. While those two curves should have been the same, the blue one reaches higher velocities. We believe this is due to two factors. First, there was probably a calibration error of the robot sensors. Second, the robot paper has limited speed capabilities and is a lot slower than an average human pace. To conclude about our work, we designed an evaluation platform for near-collision human-robot interaction that is safe by design and preserves human-robot interaction. With our method, no human or robot model are required. Finally, it is adaptable and generic, and it is compatible with any robot, with any tracking device, and any head-mounted display. Concerning the pilot study, we notice limited perception bias. In the end, the study merits further investigation. Our future work will be twofold. First, we plan to improve the immersion of participants thanks to additional devices for haptic rendering and sound rendering. Second, we plan to perform full experiments dealing with near-collision human-robot interaction. Our idea is to have a human following a robot closely in a virtual crowd and analyze the interaction during events when the robot performs unexpected actions such as brutal stops. Thank you for your attention.